Hello everyone, I'm Pratap here, and today we'll discuss independent increments, markup property, Poisson process, random walks. These are the core topics of CS2 and it will be required whatever we study later. Let's get started. CS2 where there are many chapters. The next one coming, that is statistical risk models. We'll talk about Weibull distribution, Bird distribution, all those distribution. All positively skewed distributions. The one name is loss distribution. Okay, that is one of the main topic in CS2. And further, there are a whole lot of topics where you will see the use of random variables. What about stochastic process? One way is time series. We'll continue the use of random variables in CS2 as well, and then when you study in CM2. Now, when it comes to a stochastic process, one of the main applications, one of the examples of stochastic process is random walk. Another important one is Poisson process, where you can go. That is the question. Starting from here, where you can go. Any other state, there is no restriction. I'll take you through a Poisson process and a random walk. There are particular cases of stochastic process. Let me write here first of all. Either you can go to this position from here, or you can go to this position. There are only two possibilities. This is called random walk, simple random walk. Let me write here any number, say for example 100 here. Okay, if I use 100 here, from 100 either you can go to 101 here. Let me write 99 here. I'm playing with someone, money game, and he tosses a coin. If it comes up heads, I'm giving him 1. If it comes up tails, he is giving me 1. It's a very simple game. Next time, whenever he tosses a coin, if it comes up tails, then I will gain 1. That means my wealth from now 100, it will move to 101. I'm playing after every minute or every hour also I can write, not a problem. Suppose this is 10, 3 minutes. Okay, every minute I'm playing one game, and that guy, he's sitting and he's only tossing a coin, and we both are seeing the outcome of the coin. If it comes up heads, then I'm paying. If it comes up tails, he's paying me 1. So my position now, if my wealth is 100, what will happen after 1 minute? It will be either 101 or 99. After 2 minutes, it will be 102 either. See, the variance is increasing. It's not stationary. Again, in time series, I'll teach in details what is stationary. Today also, I'll take a chance definitely. I will explain a bit. It's not stationary because the variance is increasing. See what will happen after another time period? And also I have to write here, otherwise there will be confusion. This is the example of a stochastic process because everything is a stochastic process. This is a random walk, but simple random walk. In simple random walk, what happens? You get one increment or you get one decrement. Okay, this is typically a player who is playing a game either winning one or losing one. That's all. There are only two possibilities, nothing more than that. Now what will happen next time? You go one time ahead, either 100 to here 100. That means if I lose, I come back to 100. If I win once again, I will go to 100. What about 99? At 99 also, if I play the game, so what will happen after another minute? I may be here, I may be here. If you see one thing here, this is 98. What might happen is after 2 time periods, after 2 minutes, I would have played 2 games with the other party, and I would have accumulated either 100 to 100 or 98, 3 positions. If you find the expected value here, that's what I wanted to say. Here my expected value is 100. There is a concept of martingale that will come in CM2. Here my expected value. Here my expected value of x, whatever x1 you write, x1 random variable, that is equal to 100, my wealth. Okay, my exact wealth, expected wealth, they are the same. What about here? E of x2, expected wealth here, expected wealth here. If you write expected wealth here, because x2 can take the values 101 and 99, what are the probabilities? It's not that always probabilities are 0.5, 0.5. probabilities could be, let me write here, and the random variable, the name of the random variable here is x2. Here, this is time period 2, and this is stochastic process. This was time period 1, if you see here. This was time period 1, 10 a.m. in the morning. This is 2, 10, 1 minute. This is 3, this is 4, that way. This is your timeline, time space, x2. And x2 can take either 99 or 101. But we are not here. If we are here, we know exact value. We are here, and now we are actually predicting the future. What might happen after 1 minute? While playing, I'm thinking that. Okay. So at this point, I'm here only. I'm not here. And now I'm predicting what might happen after 1 minute because I'm gambling. I'm playing a game. So now I'm thinking there is a probability that I will win. There is a probability that I will lose if it's a fair game. And if the probabilities are up, I'm not saying probabilities are always up. If they're up. And in that case also, the name is symmetric. Let me write symmetric simple random walk. In that case, when the probabilities are up, expected value you can find 101 multiplied by half expected value 100. My expected value will never change. In a random walk, what will happen? My expected value here is 100, here 100, here 100, here 100. Expectation will never change. This is constant. And this is one condition of stationarity. Again, we'll come across this one. Remember in time series, one condition of stationarity is the expected value must remain constant. Okay. Now you see, it's if you want, you can check here also. See here, it could be 98, 100. And here also there is a probability 100, 101. If you win, you go to 102. And here there is a point probability. Here there is a probability 0.5. Here there is a probability 0.5. Here there is a probability 0.5. Okay. So from here to here, when you come through all the probabilities 0.5, 0.5, 0.25 multiplied by 98. You find this 0.25 multiplied by 98 and 100 probability. This is the chance total. I'm starting from here. Okay. And here also 102 probability. Again 0.25, 102. You find like this. You see that. And here 100 multiplied by this probability or this probability, right? So I think this is 0.5. So if you find this, again you will get 100. So my expected value is not decreasing or increasing. My expected value is remaining the same. How about the variance? But the variance is changing. Acha, now, this is very important for you. You work in data science or quant or pure actuarial science. See, this is something that is intuition you need to develop. See, I'm saying you, again, this example, I'm not saying you on my behalf or from any other book. This is an actual CM2 example, probably CM2. Yes, CM2 only. See, what they say is, suppose you are standing on a never-ending ladder and you are here, okay? And these are the steps. You are going one step at a time and he's touching a coin. Okay. Now suppose he is at 300 level, 300 steps from ground. It's a never ending ladder. Okay. Suppose 1000 steps you have. And every time he tosses a coin, if it comes heads, he's going one step up. If it comes down, he's coming one step down. So this example, this is actual science example only. It was given in CM2 material. Okay. So if you go through that, you will get it. What they say, suppose he tosses the coin after every minute. You leave this place and you come back after 1 hour. 1 hour means he must have tossed how many times? 60 times. That means because the probabilities are equal, we are talking about symmetric simple random walk. So he must have got 30 heads. He must have gone up 30 times and down also 30 times. So they're cancelled. He is at the same position. Now you are expecting, if you leave this place and somewhere here you are expecting, once I will go back and see that guy, where you will be. You think that, okay, 60 times because he's either going up one step or coming down. He must have tossed 60 times, 30 and 30 they cancelled, one up, one down. Not necessarily that way. Up, up, down, down, up, down, or up, up, down, down, whatever way it's possible. I mean, maybe 10 times up, then 10 times down, then one type up, two times, whatever, on an average. Okay. So the expected value never changes. However, the variance is changing. This is very, very important property of random walk that you need to remember now. So what is not changing? Your expected position will not change. It's like, suppose someone is 300 rupees, is gambling, gaining one or losing one. So what will happen if you come after 1 hour? Suppose he wins each game 60 times, his money will be 360. I mean, worst case scenario, I'm saying. If he wins all the time, that's fine. In the other worst case, 60, 240. Okay. Now see the range 360 to 240. What about 1 minute? It's 299 to 301. What about 2 hours? 2 hours means another 60 less, right? So with time, what will happen? The variation, okay, the variation could be any side. I mean, it will increase. The variation will increase. Okay, the variance will increase. However, the mean will remain the same. It will no more change. Okay, this is something you need to remember. Acha. Now let me go to the technicality. What is the definition? How you can write? Suppose you are here, you will be here, or you will be here. These are the two possibilities. I am not using probability now. If you use probability, you write P 1 minus P. If P is half, this is symmetric. And again, I'm talking about a random walk, simple random walk. So this probability P, this is 1 minus P. And suppose this is time T minus 1, this is time T. This answer will be this value, whatever it is. Suppose this is yt minus 1. And this one will be either you will get one increment with probability P. This is plus 1, this is minus 1. Okay. So what will be yt minus 1, or you can write xt also. There are many ways you can write. I'll say you another way. So here yt will be equal to this is one way, easier way, yt minus 1 plus either one or yt minus 1 minus 1. So we can write yt is equal to yt minus 1 plus 1 with probability, right? So this is a probability distribution, okay? Plus yt is equal to yt minus 1, whatever, plus this probability, 1 with probability p, 1 minus 1 with probability 1 minus p. Now if p is 0.5, then this will be symmetric. Otherwise, this will be normal, simple random walk. Symmetric means P will take 0.5. But how we define in stochastic? Now, next time you can be either here or here. These are the two possibilities. After that, you will be either here. So you can go here or you can go here. So the derivation I will do now, simple derivation, but yes, for the new starters, sometimes they feel difficulty. So like this, these are all the possible ways. Here I didn't draw a state. What will happen that way? If you continuously draw, you will be needing infinite number of states. Okay, that's where for the first time I'm showing you one infinite state stochastic process. Let me write. The state space is infinite. First of all, the time space. This is a discrete time stochastic process. And states are infinite here. Infinite number of states, because both sides it's never ending. What about this? If states are infinite, it will never end. Okay. So how can you apply this to a gambler? So there where we apply two states, one is we'll make it finite with boundary. Okay, boundary conditions. We'll make it an observing one and reflecting one. The finite version. Okay, we'll use the finite version here this way. This I will explain now. One observing and second one is reflecting. Now you have to know the state diagram also. State diagram means suppose any number. Let me write one here, then this will be -1, this will be -2, this is 2, 3, 4 this way. If I write 1 here, parallel you see 1, 0, -1. So what will happen is, from 1 you can go to 2. I mean, here also there is 3, 4, but in a stochastic process, from any state you can go to any state. But in a random walk, either 1 up or 1 down. That is the property. Okay. So this is time 1, time 2, time 3, time 4. This is the stochastic process only, but discrete time, and state is infinite here. Here I have to write dot 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 here. So corresponding to this, let me write the diagram. That's very important, because that will come time and again. It's not only once, it will come once again. Then -1, 0, 1, 2, 3, 4. Here also -1, 0, 1, 2, 3, 4. Now the state diagram, when I write from 1, it can go to 0, right? From 0, it can go to -1. How can you represent? So let me write here. You can make it horizontal, okay? When you are making, even if you write this way also, no problem then. But yes. Now suppose this is my 1. This is 1 here. From 1, I have only 2 choices, right? If I win with probability P, see, this is probability P. From 1, I'm going to 2. From 2, where I can go? Suppose at 2 you are here. You are here. Where can you go? 3, right? You are seeing this state diagram. We consider 2 time points. In diagram, I can show only 1. At 1, what will happen? At 2 also you can write. So I'm considering time 1 and 2, or 2 and 3, 3 and 4. Otherwise, there will be confusion. That you need to remember. Okay. So staying at 1, I can go only 2. If it's any stochastic process, this is also possible. But here this is not possible, because this is random walk. So what will happen? Only one increment or one decrement. That's all. So what I will do is, I'll go back. This is not possible. Only this is possible. If I win the game, I'll go to 2. How about not winning the game? Then I will go to 0. From here, if I'll not win the game, I will go to -1. If I'll not win the game, I'll go to -2. These are probability 1 minus p, losing the game. How about winning the game? From here I can win, I can go here. Here I can go win, I can go here. Here this is p, this is 1 minus p, this is 1 minus p. This way it will continue. Now you check at 2, either you win with probability p, you go up to 3. At 2, if you lose with 1 minus p, you will come down to 1. And I will write here dot dot dot, here also dot dot. And this stochastic process is called a random walk. This is particular case of a stochastic process. Okay. So this one is used in a stock market also. The limiting form of this, that is Brownian motion. But now this one, what we will do is, because it's infinite, it can go either way. There is no stop here. There is no stop here. Okay, we'll create artificial boundary. Boundary means we'll make it finite. How can we make it finite? That I will show you now. We'll make it finite this way. Suppose one of my relative is playing game. Okay, I will say, see, I can give you 100 rupees. Okay, if you now you are at 50. If you reach at 100, then you need to go with me. Even if you reach at 0 also, you have to go with me. I will not help you. If you are broke, I will not help you. So now he is at 50. What might happen is, he will go to 49. He will go to 48. That way, time will come. He will come to 0. He might win sometimes, but ultimately he might go to 0, right? What might happen is 51, 52, 100. He is quite happy here. He is not happy here. But once 100 reaches, next time what will happen? He will stay at 100 only. That means he is absorbed. Absorbed means what? 52 probability P, 51. You can write half up also. P, that's fine. P, that's fine. But what about here? At 100 state, he is already 100 rupees. He is not allowed to play once again. So here what will happen is, he will be absorbed. He will not be able to further play. He will lose here 49, 0. So that way, what will happen is, these are the probabilities I'm writing. So one realization is, you will come here 0. After 0, next time what will happen? Next minute, if you see his state, because he is no more playing, he will be at 0 only. So if this is the time t, that means probability of xt plus 1 will be 0, given that xt 0. Suppose he comes to 0, I can draw a stochastic diagram and I can show also the full diagram, but that will be a little complicated. Okay. What is the probability here? In absorbing state, 100%. However, I mean, he is at 50. Suppose instead of 0, if I write probability of xt at any time is 50, what is the probability that xt plus 1? It will be either 51 or 49 with probability. So I can write two probabilities. Okay. This will be probability P, probability 1 minus P. Twice I can write. Instead of writing this way, if it looks complicated to you, xt plus 1 will be either 51. If xt is 50, there is a probability. Probability of xt plus 1 will be equal to 49 when xt is 50. There is a probability 1 minus p. It could be half, whatever, 0.7, 0.3, but there is a probability. But here there is no probability. There is 0 to 0. 51 to 50 there is a chance, but 0 to minus 1, because minus 1 doesn't exist. Okay. You are 0, you are broke. Once you are broke, you need to go with me. I will not help you with another 1 or 2 extra. I can do that for you. How about 100? Even if you get 100 also, same thing. This is called boundary, setting a boundary. Otherwise, what I can do is, if even I'm a gambler, okay, I want him to play, my relative to play, I say, never mind, go ahead playing. Whenever you reach 0, I will give you 1 from my pocket. So what will happen whenever he reaches 0? The proper definitions you can see technically if you want to remember. I'm just explaining the concept. So 0 to 1, 100% probability. What about 0 to 0? 0 here. This is what you need to remember. Reflect. He will reflect back to 1. Then he will start playing from 1 to, again he might win. Again, if he comes back at 1, suppose, I help him with 1. Now he is at 1. Okay, he wins. Again he loses. Again I will give 1. I will bring him back to 1. Okay. Then again he might go win again. He might play, more. Okay. Here also I can set a boundary. So if I set a boundary, at that boundary, what I can do, either I will encourage him to play by supporting, by giving him more money, or I can say it's all over. Let's live here. These are the two options. Okay. These are the two boundaries. Otherwise, it will be infinite. So if it's finite, then always you can draw a diagram. But remember, what I want to say is, these p and 1 minus p is, suppose 51 to 50 is 1 minus p, all probabilities you can write. So these probabilities won't change. Where probability will change? In the boundary, 0 to 0. 100% if I'm not supporting. If it's observing, if it's reflecting, 0 to 1 probability is 100%. Okay, only at boundaries you have to write 0, 1 probability. Otherwise, everywhere it will be P1 minus P probability. Okay. For the proper diagram, I have notes also. I'll give in the link. Okay, proper note. Just remember, I'm explaining now one important concept. Again, this will contribute for you to learn more about stationarity. Okay, because there is a technical theoretical definition of stationarity. Let me write the stochastic process. The stochastic process applications, typically, you are a data science student, you are AI student, statistics, actual science, whatever you study. What happens is, you have in time series, it contributes 20% of CS2, 20%. Can you imagine? What we will be doing is, suppose we are standing here, we are here, we are here, we are observing monthly. We have this data. Monthly, whatever you want, you can say this is we are January, right? January. 2026. This is December 2020, monthly data. Okay, whatever data you want, you take it. Stock price, let me take stock price. This is November, October, September, August, July, June, all that. Okay, we have this available, this data available. This is stochastic process. So once we are here, we have this data available. Okay, whatever the gap is, monthly, hourly, every second, every year, doesn't matter. Ultimately, I'll write using numbers. Okay, I'll start with 1. Suppose 1, 2, 3, 4, 5, 6. In this example, I'm saying, suppose I have data up to this 7, 8, and I need to forecast for 9. So this data I have. So what I will do is, suppose this is 125, 131, 130, 128, 141, 138, 145, 158. Now, using this data will be my sample. This is called one realization. Whatever way the market behaved already. Okay, I'm here means this is my sample, this is my past data. This data I will take to predict the value here, and we'll study in time series. That will be the next topic after this. We'll again, maybe I'll get a chance to say more about this. So using this data, we'll have a one step ahead forecast. We'll forecast for February 2026, March 2026, April 2000. This is called one step ahead forecast. This is called two step ahead forecast. Standing from here, let me draw the diagram also properly, because sometimes there might be a confusion. Though I drew the diagram thinking that I'm using this data, but more than the data, where we are staying here will forecast one step ahead, will forecast two step ahead. So, okay, when you forecast, like for a random variable, we use either a Poisson distribution or a binomial distribution or a normal distribution, okay, Weibull distribution, Burt distribution, gamma distribution. All these distributions we use, okay, positively skewed mostly for loss distributions, for arrival pattern, for waiting time, for lifetime, for all this. I mean, even in actual sense also, there are a variety of like 20, 30 ways we use. Now, how you can use a stochastic process. So if you want to use a stochastic process, then we have to use not x values. Here xt is a stochastic process, and this is called one realization. So these values will use. Once you use these values, the name of the models will be autoregressive process, AR, MA, ARMA. You will see in time series ARMA, ARIMA, all that. So we'll take always a stationary stochastic process. The data comes in a non-stationarity way, but you can only forecast the stationary data. Okay, so you have to transform to stationary. So you have to know what is stationary, otherwise you will not be able to do that. So what is stationary? What is a stationary time series? So there where students get confused and they lose interest, but it's very practical. It's very, very practical. So you need to understand what is stationarity. That will come. Even here also it's there. Today also I will discuss stationarity. It's not that in time series. What is stationarity? This is a term, even in interview also they will ask to know, really you developed it, conceptually you know, so that you can apply in practical situations, or you just did a book work. Okay, that they will check for sure. Stationarity is very important. One concept that will come also in Poisson process, I will discuss. This is the next part of today's class. But yeah, stationarity means what? The joint distribution. Let me just write here. The joint this is stationarity. Suppose you consider any 2 points or 3, 5, whatever. I'm for simplicity, I'm taking 2 points here. After 100 years, also, the joint distribution of 2, 3, 4, whatever. Suppose here the times are 1 and 2. I will write the joint distribution. You know joint distribution from CS1, x1 random variable, x2 random variable. This is time after 100 years, 101, 102. So I'll write a joint distribution of this. What are the states and what are their probabilities? Joint distribution, okay? Two random variables. If you consider xy, we write x can take values 1 and 2, y can take values 1 and 2. What is the probability here? Whatever way we write, right? Row, column, total, some probability will be 1. But that joint distribution and this joint distribution, they should not be different. The joint distribution at 1 and 2 or 1 and 3 should be same. The statistical properties at these points and after t time period, t could be anything, they must be alike. That's what they say. So it's very difficult to study it and to do it in practice. That's why we study weekly stationarity. You are here, random walk, still I will take some time, and this diagram I will give you, otherwise I will not be able to complete. Now see, you are here. Now you want to go to here. Okay, suppose, is it possible or not? This is the one you get in the examination. More importantly, suppose you are at I and you want to go to J in n steps. That means suppose this is time 10, this is time 20, and you want to, now you have some amount 100, you want to make it 102. Is it possible? This is the question. So how many times you will play here? You will play 10 times here. So what will happen is 10 times 1, 2, 7, 8, 9, 10. So what will happen is out of 10 moves from 100, you can get 6 wins here, 101. I mean, I can write all the states, but it will be big, right? I'm just writing, suppose like this. If you think that I'm not drawing the states, so from 100 you win, you go to 101 here. This is 100, right? This is 100. And you go to 101, win once again, 102, then come down 101, then 100, then 99, then 100, then 101, then 102, then one down 101, then again 102. How many times? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 times, can you make 102 from 100? Yes, 6 wins. So what I want is, I want 6 wins, not necessarily in any order. And 4 times I can lose. In that way, what will happen? I will get plus 6 here, minus 4 here. So next net gain is 2. So I have 100 now. I can make 102. Yes, it's possible. In 10 moves, I can make 100 to 102. That's possible. What about 100 to 105? Let me try. I don't think it's possible at all. I don't think I can't make 100 to 105 because this is even. Okay, let's keep it 10 to 20 only. This is 10 time, okay? And this is 20 timeline. This is time space. Now we are at 100. Can we make it 105? That is the question. 105 from 100, I is 100, J to 105. So 5 increment. 5 increment means 10 moves you have. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 times you will play. Okay. So what will happen? 6 wins will give you 6, 4 wins. Suppose you win 8 times, lose 2 times. So you will gain 6. And you will go from 100 to 106. Can you go 105 from 100? No. Because if you win 7, you have to lose 3. So your net gain is 4. If you win 9, if you lose 1, your net gain is 8. You can never go to 105 from 100. It's impossible. So what you need to understand here is, if this is even, the difference should be even. That way we say mathematically parity is the same. Parity means if this is even, this is even. If this is odd, this is odd. Odd means, for example, suppose you want to make, you have three moves. You can go from 100 to 103. 3 times win, that's all. If you want to get 100 to 105, you have to take it 10 to 15, 5 wins, that's possible. Or 10 to 17, 10 to 17, 7 moves, it's possible. 6 win, 1 lose, okay, net is 5. So if this is all, this all is possible. The difference is all possible. If this is even, this must be even, so that their parity will be same. So what we are saying here is something like this. Suppose you want to make from I, okay, to J. this much. So you want to make it to j from I. So what is the net gain? The increment. So you want to have an increment of gain of j minus I. In suppose here to here, this is t, anytime t, this is t plus n moves. Okay, so in n time periods, 1, t plus 1, t plus 2, t plus 3, t plus 4, t plus n minus 1, t plus n. So each time either you gain 1 or you lose 1. Okay, that way ultimately we want to be here. From here to here you want to go. You want to make it j from I in n moves. So let me write, if n is even, then j minus I also it should be even. And if n is odd, j minus I also should be odd. So what will happen ultimately? You add even plus even, n plus j minus I. This should be even, because even plus even is even odd plus odd is also even. So this total is even. That is one condition you need to remember. Okay. So we write the probability. What is the probability that you go from pi to j? This is going from pi to j in n steps. It's 0 first of all. Okay. Under what condition 0? We'll write here. But what is that probability? We'll write here. Okay. This should be even first condition. Second condition, this should be less than n. Okay. J minus I, this gain should be less than n, because suppose we want to make 100 to 121 in 10 to 20. How it's possible? Suppose I have a wealth 100 and somebody says you make it to 121. Every time I get either one or I lose one, and 10 moves are applied, 10 tosses are applied. In 10 tosses, if I win each toss, then also I will go from 100 to 120 only. I can never go to 121. So if the number of gains I want is more than the number of attempts I'm allowed to play, then though it's impossible, right? So when it's impossible, j minus I should be less than n. Okay. If j minus I is not less than n, equal to n also possible. Because if they're equal, what will happen is, in 10 moves, I want to make it 120. That way. Possible. I mean, there is a chance that I win all. That way it's possible. There is a possibility. Okay. So so if you add n both sides, this is a derivation actually. If you n add both sides, it will be 2n. J minus I plus n is less than or equal to 2n. This is even. So write it. So remember, Pij in n times. What is the probability that you go from I to j in n time periods? That will be equal to 0 otherwise. And what is the probability? We'll find this now. We'll derive this. Under what condition? N plus j minus I is even. This is one condition. Other condition means this is n plus j minus I less than or equal to 2n. Under these two conditions, this will derive. Okay, let's derive now. It will take 2 minutes. So if you see this one here, this diagram, I want to make from I to j in n steps. Go on winning. Winning probability P. Winning probability is P. And I will win, suppose, U times U up steps. These are winning. And D down steps. These are losing. So total steps are allowed is n. Next time if I go down, this will be 1 minus P. So this is the 1 minus P probability, or Q if you want you can write. So these are the probabilities. But U steps in total, U win and D down steps. So every time you win, there is a 1 minus P probability. You go down with 1 minus P probability. Okay, these are the probabilities. So out of n steps, you need to win P types. Sorry, you have to win U up steps. That's winning. P power U, Q power n minus U. This is a binomial. Okay, so that means n are allowed, n times you need to play. Out of that, U of steps are there with probability P, and n minus U down steps are there. In total, n steps, U plus n minus U, n. Okay, it's like tossing a coin, winning and losing. So what will happen? You want to make from I to j, I to j. So total what will happen is j minus I is what you need. Okay. So what will happen? Suppose you want to make from 100 to, I started with this 100 to 102, 100 to 102 in 10 steps I wrote that time. If you remember 10 to 20. So my n is here, 10, j is equal to 2, I is equal to, j is equal to 100 to I is equal to 100. So my net gain is in 10 steps is this. Okay, so n is equal to 10 and j is 100 and I is 100. So I want to gain 2 in 10 steps. So the number of up steps, if you see, because this is even, this is possible. So six ups you have. Suppose all ups you have and 4 downs. So you came here that way from 100 to 102. 6 wins and 4 total. You lose 4 times. Okay. So 6 plus 4, 6 plus 4 is 10. So 6 plus 4 is 6 minus 4 is 2. 2 gain plus, but 6 plus 4 is 10. Okay, total. So if you have u up steps and d down steps. So if you see, if you find u plus d, number of up steps, down steps, that will be equal to total number of steps. So in our case, 6 plus 4 is 10. 10 is n here. This is n. T to t plus n. How about u minus d? Suppose I win u times, I lose d times. My gain is j minus I. J minus I will be equal to, the gain is number of up minus number of down, because the number of up is u, number of down is d, right? So they're equal. So you can add these two. 2u is equal to n plus j minus I, and u is equal to n plus j minus I by 2. Whatever, u, d you get. Okay. So using this u and d, you can use this binomial probability. That's all. So let me write here final formula. Out of n, I want u wins. Okay. Winning probability p times I need to, and 1 minus p, and p, this is the formula, right? nx p power x q power n minus x. So nu p power u q power n is matching here n minus u. This is the probability. And this with u you know already, n you know, n will be given in the question. U you know how many up steps, how many down steps from here. What is that u? We found here u. U is n minus j. N is given, ij given, right? Suppose in our example, n was 10, j was 102, I was 100 divided by 2. So this is 2, 6, u is 6. I got u 6, d 4, n 10. So we find the probability. You put everything here. You put everything here, you find the probability. What is the probability that you will go I to j in n steps? Okay. So let me put here 10, 6, 10, 6, p power 6, q power 4. This is the probability. Okay. And if p is given half, q is given half. P will be given. So if p is given, you know q, then you will be able to evaluate this one. Now using diagram also I can do this. Using diagram also I can do this. Okay. I can do this. 6 times up, 4 times down. How many ways it will happen? I have to show these many paths. 10 factorial by 4 factorial, 10 minus 4, 6 factorial. So many paths will be there. Okay. So 7, 8, 9, 10 divided by 4, 3, 2, 1. So this will be a lot, right? Even if you like, I can show you something like this. Not for this problem. This is over. I know this is very, very simple. But what will happen is, suppose you want to see all paths. If you don't know how a stochastic process operates, you will have a better idea. because stochastic process is the backbone of your career, and also random variable. If you really understand random variable, these two are important because all the statistical model will be through these only. So now see, I will show you all the path 10, 11, 12, 13, 14. Okay. So n is the gap. Okay. From 10 to 14, I'm allowed to uh, play 4 times. 1, 2, 3, 4. 10 to 14. N is 4 here. And suppose I'm here at 100. This is 100. And 102 in 4 times, I want to make 102. Okay. So I is 100, J is 102, N is 4, and number of steps U minus D. Need one lose I need, so that one loss, I mean, if I lose once, win 3 times, I will reach 100 to 102. That we know. But how? How many paths are there? These many paths are there. Each time what will happen is, I have how many wins? In each path, how many paths are there? My paths are 4 to U is 3 here, 4, 3 number of paths are there. Okay, 4 factorial by 3 factorial, then 1 factorial. That means 4 path I can draw. I can show you 4 path. Each path, what will happen is P power 3Q. So 3 times win, 1 times lose. I will show you how many paths. Total paths I will show you 4, right? Okay. So one path is 100 to 102, right? 100 to 102 here. How I can show? I can show this way. You win. From here you win. 100, 101, 102. Okay, okay, I got it. I got it. You win. Because you can't stay here. I will go to Poisson process now. You lose here, you win here. Possible? 3, 1, 2, 3 wins, 1 lose. Ultimately, you see, this must be satisfied. 3 wins, 1 lose. Why you are multiplying? Instead of adding this probability, see, when I say this and this, you are multiplying probabilities. But one path, then the next path probability will add. That's where you are adding this how many times? 4 times. That means multiplying by 4. 4 PQ Q. 4 is this. Means we're adding all these probabilities 4 times. I'll show you another one. 4 path I want in total. Okay, I will lose. Again, I will lose 2 times. But I'm losing once. So I can draw this. If you go here, you can never reach 1, 2. I'm confusing. Am I confused? Little bit. Okay, go back. So now what will happen? I came from here to here. Once only I can lose. Then win. Then win. Then win. This is another path, probability. Another PQQ. If P is 60%, that way you find this one. Third path. You can lose once, right? But third path will be, let me change my ink now. Ink I will change. Third path will be, you win or no. No. You win. No worries. Acha. You win. You lose. You win. You win. This is one path. Third path. Fourth path is, you lose once. You can't lose here. You can lose only once. Okay, you lose here. You lose here. No, 2 times no. You win here. You lose here. No, once only you can lose. So that's over. You win here, win here. You win, lose, win, win. 1, you win, you here also win, here also win. And from 103 you come 102. That is also possible. See, ultimately what we want is, you have to win 3 times, lose 1 times, and finally you have to reach here. That's what you need to check. How many path? This is 1, this is 1. Okay, this is 1. 1 down, 3 up, 1 down, 3 up, 3 up, 1 down, 1 down, 3 up. So in a stochastic process, with you can go only 1 up or 1 down each time. This way it's possible. This probability we are finding. That's all. It's over. Now I'll go to Poisson process. Okay. I wanted to complete in 1 hour. I know in live classes, I can't make it 100% effective for you. But unfortunately, we have to accept little bit of problem because a lot of things are connected. Sometimes, due to different problems, they don't allow whatever way we want. But yeah, let's go with that, whatever is available. Now, remember I started with stochastic process and I said these are the two examples we'll study. One is random walk and one is Poisson process. Poisson process and independent increments are so important. Stochastic process, this is also a stochastic process. But in stochastic process, you go from anywhere to any other place. In a Poisson process, what will happen? So suppose you start from here, either you can go here or you can go here in case of random walk. This is random walk. How about Poisson process? This is also discrete time. In case of Poisson process, what will happen? Suppose you started with 100 here. You know that you will be at either 101 or 102. But in case of a Poisson process, what will happen? If you are at 100, suppose we see each day movement. Okay, suppose I'll write you play once each day. Here, the number of claim an insurance company gets. Suppose today insurance company closed with 100 claims. I'm talking about general insurance claims. So number of claims here at time 1, number of claims, or time 0, let me write time 1. Time 0 means it should be 0. Poisson process definition starts with 0. There is a reason. Again, I will not go to that, but yes, I want to start from 0. Otherwise, that will create another problem. So let me start with 0 here. 0 to what you can do is either you can go to 1 or -1. One step or one step down. What about Poisson process? In Poisson process, 100 to you go lambda. Lambda is suppose 10 claims, 110, 120. Again, I'm taking homogeneous. So let me bring it down. And I'll introduce one more. So Poisson process is a counting process. Counting process never go down. You count. Suppose I start class, no one is there, then every 5 minutes I will check. So 0 to 2 students, 5 students, 7 students, 10 students, what will happen is when I'm counting, the number of students will never come down. It will go up only, right? Once someone enters, he will not be allowed to go out. That way, counting process will always increase. It will never decrease. See, random walk, it can decrease. A stochastic process can go down, but Poisson process is a particular case of a stochastic process which will never go down. And this is time. Time is 1 day I fix here. Every day, an insurance company gets 10 claims. That could be modeled as a Poisson process. So Poisson process increment here, I've given 10 here each day. But here in random walk, only one possible. So one time period, one is possible. Also, one time period, you can go one step up or you can go one step down. But here, no down, only up, up, up. Gets claims. This is lambda, okay? At rate 10 per day, 10 per day, at a rate of 10 per day. This is lambda. Lambda is 10 here. So let me write lambda. Here I can write this way. That means lambda is equal to 10. But what is the definition of a Poisson process? We solve this problem. That's not a problem. So you can write x, but again, let me introduce X we use. And in Poisson process, normally we use N, but N is also stochastic process. Some books, they use XT for discrete and XT for continuous. And some books, they use NT this way also and NT also. It doesn't matter. Okay, whatever way, they are the same. But I suppose here we will use NT instead of XT and T. This way we'll use. So if you are using some material or some book where they've written N bracketed 10, never mind. Okay. So N0, when I write N0, that is stochastic process at time 0. Okay. This is 0. This is 1. This is 2. This is 3. So N0 is always 0. If it's a Poisson process, this is always 0. I've started from 100, right? I've started from 100 means this is not 0. If I write this 0, I think I wanted to introduce another one here, but I forgot. Okay, I will do that, no problem. So that there will be no confusion. This only I want to make Poisson process 0. Rate I've written only 10, 20, 30. That means what will happen is, if I'm saying the claims process follows a Poisson process, okay? And normally, yes, what will happen is, and it's not necessarily homogeneous, but here if you see 10 a day, so lambda is 10, okay? So there might be 10 questions you will get in the examination, 10 variety of questions this way, but I'm writing the property. You see, it's starting at 0, and 0 is 0. And number 2 here is, it is stationary increments. It is independent increments. I'll go to independent increments and stationary increment, then I will come back to the definition. But apart from that also, importantly, NT minus NS or NT plus S minus NS, whatever way you write, NT minus SN, NT minus NS, that means what? If I write here in my example, N3 minus N0, that is N3 only, because N0 is 0. N0 is 0, that is by definition. That should follow Poisson lambda T. T is 3 here. Lambda T. T is 3 here. I've taken, what is T? How many time periods? 3. 3T. Okay. 3 lambda. So N3 will follow a Poisson distribution. 3 lambda. Poisson 30. Lambda is 10. T is 3. 30. Poisson 30. Then you can find the probability. You can treat as X. X follows Poisson 30. Okay. X follows Poisson 30, then whatever way you use Poisson distribution, that way you can use this one. But importantly, according to the definition, this follows a Poisson pattern. NT minus NS follow a Poisson pattern. NT minus NS, this is stationary. And this is independent increments, but I didn't teach you what is independent increments. Stationarity, I said you what is stationarity. So we have to discuss that one. Okay. So this follows a Poisson pattern, lambda 10 here. Now, importantly, more than, this though you can always remember the definition. But what you need to understand is what is a Poisson process. The main important properties, in one instant, you will get either one or no. That must be satisfied. More than anything else, if I teach Poisson process, I leave that. That will be like nothing. Okay, so what I'm saying is, let me copy. What I am saying here is something like this. This is my timeline. So according to Poisson process definition, Poisson process means what? Poisson process means something like this. If you consider any interval, any small time period, you think 1 second, but even it's less than a second. Okay. So what it says, you will get 10 claims, but it's not that the 10 claims you will get with the, in one interval, suppose I'll write 10 to 11 in the morning. Okay. 5 claims. Within one day also, there are different time intervals. Okay. Poisson process says if you consider a very small time interval, suppose 10 to 11 or 10 to 10 a.m. to 10.1, within that only you got 5 claims. It's not possible. They say if this is one day you are getting, per day you are getting 10 claims. That is the rate they say. That's fine. There is no problem. So many they ask me also, how that sir it's possible? You are saying you will not get more than one claim. See, the thing is, in one day you will increment. Okay. In one day you will get that increment. That is there. In one day where that is lambda. Lambda is there anyway. 0 to 10 will reach. But how you reach 0 to 10? How you reach? You reach this way. You get one claim here or no claim in one interval, one or no. In another small interval, suppose 2 to 2.1 or 2 p.m. 5 minutes to 2 p.m. 6 minutes, this interval you get 1 or 0. Another small interval you get 1 or 0, which is not in counting process. I'm talking about Poisson process. You must be knowing counting process. Counting process means what? The number of students coming to the class. There is no randomness also. Deterministically they can come also. So here randomness is there. Again, importantly, in any small time period, either you get 0 claim or 1 claim. 2 claim probability is, very, very less. It's very, very less. Either 0 or 1. Okay. Either you get a claim or you not a claim. That means suppose I am working as a customer care, where? Vodafone or Airtel customer care, I'm waiting. Okay. The calls arrive to my phone. I'm receiving a call in every second. Okay. I can get one call. That way you can think. It's not that in 1 second I get 10 calls and in a day I get 10 calls. It's not possible. Okay. So what will happen is in intervals you will get this way, 1, 1, 1. That way you will make total 10 in a day. In a day means you have so much time, right? So there are so many intervals like maybe 10 to 10, 1, 1 claim. 10 2 to 10 3, 1 claim. That way possible. Maybe you have 100 claims a day, 1,000 claims a day. There are so many stripes you can make. But in one instant, in a very small time interval, either you get one claim or no claim. That is important property of Poisson distribution. So what we say is, if I write nt plus s, or you write nt plus s like this, minus nt, okay, this is the small interval. This, what is nt plus s? Nt plus, if this is t plus s, this is nt plus s. Okay, no, sorry. This is nt plus s. This value. This is the time I've written. Time I have to write here. Here the value. Suppose, let me erase. Here I have claims. I started with 0, 9, right? Suppose I have 5 here. Somehow I got 5. This is already 2 hours past. Okay, or 9 to 10. I got 5 claims. 5 to either what will happen? I will be at 5 in the next instant, or I will be at 6. That's all. So that means what I'm saying is here consider one such instant. Here suppose here you have 5 claims already. Here after that instant either you will have 5 or you will have 6. That's what any arriving center. It could be a mall, it could be like me, I'm a customer care, I'm receiving calls from the customers. So in the next instant, see, I'm teaching you, I will see my phone, either I will get one call or no call. I will not get 2 calls. If I by chance get, that means I'm talking, there is a busy sound, time and again it's coming, not from the same person, from many other persons. That means it's not a Poisson process. It's not following a Poisson process. In one small interval, either you get a claim or you get no claim. Okay, similarly here to here, here to here. That is your Poisson process. So here I'm not talking about nt plus 1 minus nt. T plus 1 when I say, that means I'm talking about one time period, that is one day here. See, our time period is one day. In one time period, rate lambda we have accepted. That lambda we get increment, Poisson process. It will go on increasing by 10 each day. That is there. That is lambda. And that way we solve the problems. But what is the definition of a Poisson process or Poisson distribution? I mean, you must have studied in Poisson distribution, Poisson process in CS1. What it says, in a very small time interval, either you get one increment or not. That way, it will go from 0 to 10. Not like once many, then not. I will give you another example. It happened also. You might smile if you listen this example. This happened really, I was sitting. So suppose this is a clinic. A doctor is sitting. A doctor is seeing patients. Okay. This is doctor and doctor is seeing patients. Now patients are coming one by one. Again, this is arrival pattern and this is not by appointment. This is on a clinical setting. This is a doctor's clinic. So even doctor has no idea how many patients they will come here. So once I was sitting here, this side actually on chair. So three persons they immediately they came and they occupied the seat. I'm sitting here. Then the doctor, because the doctor knew me already, doctor called this patient. Okay. And then all the three they went near him. Doctor scolded them. They said, "Get out from here." And he said me, "You know what? Here the trend is one patient is one. With the patient three or four, they come and they make, make me trouble. I think that there are so many patients. Okay, that way I plan, but it's not. So whoever the patient I want to see, not everyone. Why others will come and say? So this is not three. You don't count it three. This is one arrival. So one patient arrival. So that is also Poisson process normally. In a clinical setting, that is random events. And if you see any instant, either one will come or no will come. Okay, that's Poisson process. But in a time period like lambda, we are taking rate in one time period. So when I write t plus 1 minus that we can expect lambda at a rate of lambda. Okay, but here 0 or 1. Okay, so this is 0 probability we have, and this probability, because n t plus s is t plus time s is very close to t. This is t, this is t plus s. But this is 0 and 1. The gap is 1 here. Within that 1, this is happening, this small stripe. If this is 0, this is 1. This is one time period. Okay, here lambda. Lambda is 10 increment. But how about this small? In this small, either you will have one increment or no increment. That's what Poisson process is. So this is 0 or nt plus s minus nt is equal to 1. Okay. And the probabilities also there is a definition. Okay, full definition. So either, but if I write probability of nt plus s minus of nt, that is equal to 2, this is negligible. Okay, negligible means we use order symbol there, but here you can write probabilities. You can define with what probability, with what probability. Total probability is almost 1 here. Order of h is there only for this. This is very small chance, very negligible chance. So that is what the Poisson process is. Again, for your information, Poisson process is not over. I'm only introduced, because in the next chapter, 4 definitions of Poisson process they've given. So what I discussed now, even I didn't discuss the waiting time property. Okay, waiting time will come once again. Independent increment is also there. Okay, I'll introduce the increment today. Again, we'll go to Poisson process. I introduced in the CS1 way without any derivation. I just introduce the definition of Poisson process in CS1 way. But there are 4 definitions in CS2 that will come. Okay, all 4 will study one by one. And importantly, when you say someone that I know stochastic process, remember these two. I'm saying you now. Chapman's Kolmogorov equations, 4 equations are there. These 4 equations will study. Okay, forward differential equation, forward integral equation, backward differential equation, backward integral equation. You need to solve all these equations. Okay, if you really understand this, you will be at a level you can model anything in the world. It's so awesome. It's so interesting. The second one is time series. Oh God, time series. If you really understand time series, all this AR, MA, ARMA, ARIMA, SARIMA, we don't have. I mean, also we will study only linear time series. Okay, we'll go up to ARIMA. There are 2 chapters here. This is huge. Stochastic process knowledge is huge, I'm saying. But yes, inch by inch we'll go. Today, I'll introduce my last topic, independent increments. I know still you can, there are a lot you can ask, but yes, whatever is possible, let me do that. Independent increments. Acha, independent increments means what? I have a stochastic process and these are the values at time 1, time 2, time 3, time 4. Normally we write this way. When you go to continuous time, you will see this way. But many books, they write in discrete time also both, sometimes continuous times also both. It doesn't matter. So this should not be a confusion for you. Now, what is independent increments? Okay, x5. That means you know all these values. Where are you? You are here. This is your stochastic process. And you are here. Already you are here. You are somewhere here. 1, 2, 3, 4, 5. This happened. Okay. 1, 2, 3, 4, 5. And you have 6 also, 7 also. Where are you? You are here. That means you know the values up to 5. You know how the uh, world moved through. When I say states, these were the possibilities. Okay. And once you have a realization path, you say it's one realized path. That means something could have happened, but already happened. Okay, we'll not worry whatever has happened. We'll model for the future. We'll model for the future. Now we are standing here. So when we are here, we are here. Okay. This is my oval face. I know. I know what happened here. That means I know how the world moved from here to here, here to here. It could be same. I'm not talking about a Poisson process, any stochastic process. It could be anything. So I know how the world moved from where to where. Suppose it was at 90. Now it's at 100 to stock price or whatever you say. Okay, at this point. So now we'll predict for future. So that means because I am here between 5 to 6, this is my past data. I know the realized path, whatever way it happened. I know the past already. Okay. But I don't know future. For that, I will model, not using Poisson or binomial distribution, but using, as I already said you, mostly when you talk about time series, that is the best application. Okay. But before going to that, what is independent increments? I'll talk about x6 minus x5. Okay. That means, suppose I'm expecting 108 tomorrow. I don't know x6, right? So I'm thinking suppose I have a portfolio, my value is 102. If I'm expecting 108, I'm expecting an increment of 6, that increment of 6, okay, for tomorrow. Not the value 108, the increment, this increment, x6 minus x5. I know already up to x5. This I have, this information 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 I have. This increment, this x6 minus x5, this is independent of this or dependent to this? This is the question. Independent increments means what? This increment is independent of whatever way the world happened. Okay. Or dependent. That's what you want to know. Independent increment always possesses Markov property, but otherwise it's not true. Right? Now, not only this increment, sometimes suppose you are thinking about day after tomorrow, 100, 110. or 115 means increment of 115 minus 102 from now, where we know up to this there is increment of 13. That increment, it could be, see, two increment also you can take, x7 minus x5. This is also increment. This increment is dependent to this or independent to this. That is the definition. You go through the original definition. So probably you will get something like this: xt plus 1 minus xt plus s minus xt, or x plus t1 is independent of x1 up to xt. You will get like this, is independent to all this. This is the definition. This is independent to all these values. That is the definition of independent increments. Okay. Now, when I talk about independent, suppose, see, there are two things: x1, x2, x3, x4, x5, x6, they are independent. Means x6 is independent to x1, x5 is independent to x4. Remember, I started with tossing a die. Okay. Even in random walk also, when I said you will get an increment 1 or minus 1, okay, each time, their IID, independent and identical distributed, because I will send you the complete notes, or you might get it in the material. You try to understand. I'm explaining you what is this. Okay, IID I left that time. I forgot to say that. But remember, independent increment is this. And the important properties I will not extend. Probably we can have a doubt clause also later. So remember this: independent increment will imply, this is not over, independent increment would imply Markov. Markov means one step dependency. Okay, but Markov is not necessarily independent increment. There is a result. Okay, this one also, one example is also given. You can do that. So because you will go through the exam questions. Even today also, I had so many exam questions open, but I was unable to do. But yes, my focus is on exam questions, and the R program also for this one we have to do, right? We have a lot. But I think whatever I'm explaining you, from that you can develop whatever is required for you to develop up to that level. So here, coming to the Poisson process definition, remember, so the increments here, I was talking about increment, the increment, this increment will not only follow uh, a Poisson distribution, but also the increments are independent, they're stationary. Independent increment means what? There is no link. They are different properties. So when we talk about Poisson process, the increment will follow a Poisson pattern. The increment is independent. The increment is stationary. Poisson process will start with 0. And Poisson process uh, is a counting process also. Counting process also definitions. It's monotonically increasing, all that, whatever. But counting process, we never say it will start with 0. Counting process, there is no such independent increment. There is no such condition of stationarity. There is no such Poisson distributed. Again, there is a meaning, because if I talk about more about this, it will take another 2 hours. Poisson process itself, okay, if you want to understand, it will take time. Okay, like I'm saying, there are 4 definitions. I will again bring this one, but next time probably we'll be able to do all 4 definitions in half an hour, because other 3 definitions, they're linked with the chapter itself. Okay, uh, whatever we'll develop later, we'll form differential equations and solve differential equations. We'll go to continuous time. We'll study Markov jump process, Kolmogorov equation, a whole lot of things. Okay, that will be next level. But these are the fundamentals you develop. CS2